Hi, welcome to Chapter 4, Alkanes and Cycloalkanes. In this chapter, we will be describing the chemical structure of alkanes. We will be identifying the parent chain and substituents of an alkane. We're also going to go through the 4 steps involved in assigning systematic or IUPAC names to chemical compounds, including bicyclic compounds. Explain how to avoid duplication when drawing constitutional isomers. Defining what is heat of combustion, describing how it's measured. Sources of alkanes, including processes for converting crude oil to useful hydrocarbon. We're going to discuss the importance of perspective when using Newman projections. We're also going to learn about Newman projections, by the way, to illustrate the conformations of alkanes. We're going to describe staggered versus eclipsed conformations for ethane and similar molecules and the difference in energy between them. We're going to compare and contrast the potential energies of different staggered and eclipsed conformation of butane, describe the significance of strain in cycloalkanes, describe chair and bulk conformation, illustrate chair conformation of cyclohexane, including describing what is axial and equatorial substituents, describe possible positions of the substituents in monosubstituted, what happens when we have a ring flip, and which conformation is favored. We discuss three-dimensional orientation, cis and trans stereoisomers, and lastly, some common polycyclic systems. Let's start with a little bit of an introduction to alkanes. When we talk about alkanes, we're talking about hydrocarbons, which are molecules made up of hydrogen and carbon, as the name suggests. We have a few here. We have alkanes, which have your single bonds. We have alkenes, which are double bonded. We have alkynes, and then we have our aromatics. Hydrocarbons are all of them, but then we separate into alkyne, alkane, etc. Hydrocarbons are either saturated or unsaturated. When we talk about saturated hydrocarbon, we're talking about alkanes, systems that have all of the bonds that they can potentially have. When we talk about unsaturated, we're talking about systems that have multiple bonds, rings, etc. Many organic compounds have common names that we tend to use that are not necessarily their systematic names. Systematic names are the ones used by the International Union of Pure and Applied Chemistry, or IUPAC, and those are the ones that we tend to use across different countries, across different disciplines to describe objectively the difference between different organic compounds. Some common names, for instance, we have formic acid, urea, morphine, barbituric acid. All of these, they have either a historical connotation or a connotation based on how that compound was first isolated, but none of them are the accepted IUPAC names. The IUPAC system is a way to systematically name different compounds. It includes what we call the parent name. That is, when you have a rather large molecule, the parent chain, that's going to be the longest chain that contains carbon atoms, the name of all of the substituents as you move through the molecule, and the location of these substituents throughout the molecule. For example, here we have this molecule, it has all sorts of branches, etc. So what we do here is that we identify where in this molecule can I have a line or a chain with the largest possible number of carbon atoms. If I go from left to right here, for instance, I have 1, 2, 3, 4, 5, 6 carbon atoms. If I go this route, I have 1, 2, 3, 4, 5, 6, 7, 8, 9 carbon atoms. That will be a longer chain. So that will be my parent chain in that case. Now, when you start identifying the parent chain, you can go from top to bottom, bottom to top, side to side, etc. So the idea is that you will start numbering based on where you have the most numbers, right, the highest number of substituents in that parent chain. So if I, for instance, in this case, I have 1, 2, 3, 4, 5, 6, 7, right, or 7 here, either will be 7 carbon atoms. So I have to pick which one will be the correct systematic chain. In this case, if I go with the structure on the right, I have 2 substituents, whereas if I go to the structure on the left, I have 3 substituents. That would be the correct structure that I would pick as my parent chain. Now, for alkanes, there is a way to name compounds that will tell you how many carbon atoms you have. The first 4 carbon atoms are named based on historical concept, not necessarily geometric ascension or anything of the sort. So if you only have 1 carbon atom, the parent would have METH, such as methane, methane, 2 carbon atoms, ethane, propane for 3, and butane for 4. After that, we have uh, a rather logical ascension as you move. So 5 will be pentane, such as a pentagon, 5 corners, so pentane, hexane, heptane, octane, and so on, until you reach whatever number you need to reach. The first 4, as I mentioned, not necessarily have that same system, but as you hit 5 carbon atoms and beyond, you do have that logical sense. So at this point, I would like for you to familiarize yourself with this table, because you will be looking at this very often throughout the course. Identify the parent chain, longest consecutive change of carbons. If the parent chain is cyclic, so it's a closed system, we call it cyclo. So for instance, this little triangle here, 1, 2, 3 carbon atoms, so propane, right? But because it's cyclic, it will be cyclopropane. 4 carbon atoms, cyclobutane, cyclopentane, etc. Now, once we have figured out what is the name of that parent chain, we need to figure out the name of the substituents. So here we have this chain, it has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it will be a decane, right? That will be the name of the parent chain. And then with decane, if I'm counting from left to right, I will have in position 1, 2, 3, 4. I have this guy right here. That is a 2 carbon atom system. It will be ethane, right? Or ethyl, right? Ethyl when it's a substituent, as you can see here on the table we have on the right. That will be position number 4. Position number 5, I have 1, 2, 3 carbon atoms, so it will be a propyl. And then positions 7, that will be a methyl group. Substituents end in YL, il, instead of ANE. ANE is reserved for the parent chain. That's another way in which you make the different parts of the molecule a little bit more obvious. Once we identify the substituents, we start naming them. So for instance here, a ring can be either parent chain or a substituent. It really depends on the number of carbon atoms. Here, for example, I have a 6-member ring or a cyclohexane, and I have a 3-member chain next to it. So 6 is larger than 3, therefore the cyclic part of the molecule is the parent name or the parent chain, parent cycle in this case. No, so this will be cyclohexane, and you have a propyl substituent, so this will be propyl cyclohexane. In this case, we don't have to number the propyl, we don't have to indicate in which carbon atom is attached, because we're going to assume that because you only have one substituent, it's going to be attached to position 1. So it doesn't matter. In the example to the right, you have a 3-member ring, and you have a 1, 2, 3, 4 chain, so the chain becomes a parent. So that's butane, not 4 carbon atoms, and you have cyclopropyl here attached to the carbon number 1 in butane. By the way, when I have only one substituent, if it's on one of the ends of my parent chain or ring, then I will say that that is the position number 1. I choose the lowest number for my substituents whenever possible. For substituents with complex branches, so for instance here I have, this is my parent chain here in red, then I have this substituent, I have 1, 2, 3, 4, so that will be butyl, but within butyl I have a methyl group right here in position number 2, so we're going to call this substituent 2-methyl butyl, and then whatever the name of the chain here is, this is 2, 4, 6, 8, 10, 11, so on the cane, and this is in position number 1, and position number 1, 2, 3, 4, 5, 6, so in 6, 2-methyl butyl on the cane. Some branch substituents have common names. We can use them in some cases. In others, when it's required to use IUPAC name, then we go with the system we just described. So for instance, this guy that looks kind of like a Y, that's isopropyl. It can also be 2-methyl ethyl or 1-methyl ethyl. Some branch substituents have common names, 3 types of butyl groups. So butyl is just 4 carbon atoms, but depending how it's branched, it will be sec-butyl, isobutyl, or tert-butyl. They all have different properties, so we have to be careful to name them depending on how branched it is. So properties, I mean different melting points, boiling points, different densities, different polarities, etc. So we have to be very careful and we have to be accurate when describing these. Carbons in the parent chain must be numbered. If you've noticed throughout this video, I've been numbering, right? I've been assigning numbers to the different carbon atoms. I've mentioned position 2, 3, whatever. So that's something that you need to be doing every time you're trying to name a compound using the IUPAC system. So here, for instance, we start numbering 1, 2, 3, 4, 5. You could have gone the other way, right to left, 1, 2, 3, 4, 5. The reason why it makes sense to go from left to right is because you have a substituent and you want that substituent to be in the lowest number position. So position number 2 is smaller than position number 4, right? So that's why we go that route. In the example here, in the right, you could have gone either way because literally that methyl is in position number 3, regardless of whether you name left to right or right to left. Doesn't really matter. So this one's gonna be 2-methyl and then pentane. This one's gonna be 3-methyl pentane. 3 refers to where the methyl is located. Some guidelines to follow when numbering the parent chain. The parent chain is numbered from the end closer to a substituent, just like we saw in the previous example. See how you can go from left to right, right to left, but position number 2 smaller than position number 6. So that's the criteria you're going to use. In this example, we number the parent chain so that the substituents 2, 5, and 5 rather than 3, 3, and 6 because we want the first number to be as low as possible. So regardless of whether you have one or many substituents, you're always going to shoot for that lowest possible number. In this case, you might say, well, these two are better off in position 3 than 5. Yes, but this one is better off in position 2 than 6. And 2 is the lowest of all of the numbers, so that's the criteria you're going to use for numbering these compounds. If there is a tie for the first number, then the second number should be low as possible. So I think the lesson here, right, this is very systematic, so you have to be careful to always complete, right, always do the exercise of numbering everything, considering the different combinations, and then you assign numbers to the different substituents, and you assign the name of the parent chain. This isn't something that you can just do without thinking, right? You have to think about it on a case-by-case basis. That's very important. If the previous rule does not break the tie, we assign the lower number to the group that comes first alphabetically. Right? That's going to be the last of the tiebreakers. So in this case, we have position 4 and 5, 5 and 4, so there's a little bit of a conundrum. We have an ethyl group here, and we have a methyl group here. Ethyl starts with an E, methyl starts with an M. They're both 4 and 5, so there's really no criteria other than alphabetical order. So this will be 4 ethyl, 5 methyl, instead of the other way around. The same rules apply for cycloalkanes. Same deal, you apply, you count, whatever gets you the lowest number for your substituents, that's the one you're going for. To assemble the complete name, we'll put the number and the name of each substituent before the parent chain in alphabetical order. A prefix is used if multiple substituents are identical. Prefixes are ignored when alphabetizing the substituents. This is actually a pretty important point. This is a very common mistake I noticed. Those prefixes, they don't count at all for assigning alphabetical order. Super important. So as a summary, we first identify the parent chain, then we identify and name the substituents, number the parent chain, assign a location to each substituent with the rules we just discussed, and then we list the number substituents before the parent name in alphabetical order.